Yay.
All right, all yours.
All right, welcome folks. I'm Peter, and this is Chromium C++ 201 Part 1, hopefully of 4 eventually, although I've only fully written up Part 1, so we'll see. There's a Go link on this first slide. You can get to the slide deck there. Secretly, if you change the number on the end, you'll get to the other incomplete slide decks. So if you are the kind of person who likes to look for Easter eggs, you can do that. But let me just give you an idea of what this talk is. I'm probably going to talk for 45 minutes-ish. Please feel free to type things in chat. I can see that, I hope. And also to just speak up and yell if you have questions. The idea of this is basically to do something a bit like a college class. So, you know, professor stands up in front and lectures while everyone else doesn't pay any attention, and then maybe doesn't come to class either because it's too early in the morning. The title of this kind of gives you an idea of what this is. Chromium, because this is going to have Chromium specific recommendations in it. I hope someday something like this can be public, but it will be like not just general C++ for anybody. I'll talk about things in base and stuff like that. That said, it's mostly about C++. It's mostly not about like, here's when you use base : blah, 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 and this special trick with what a web contents is. It's mostly things in the C++ language and library. So specifically C++ 14, even though that's not the latest C++, that's the one we use. And then finally 201, like I said, this is kind of college class level stuff. So you can think of this as not a 101 level class. I'm not going to be going over, you know, how do I write a for loop? But also not the super obscure stuff that you might get in a graduate level course of like, what does standard launder do? So I basically will assume that you know a little bit about C syntax, classes, and the basics of the STL, stuff like vector. But I'm not going to assume too much more knowledge than that. So if that's exactly your level, great. If that's way lower than your level, hopefully there's still some tidbits of this that are good review. So the point of this series is really just personal growth. Do whatever you need in order to receive something from this. If that means that you want to take notes on things that I say that are interesting, or pull the slide deck up, that Go link, go/chromium-cpp-1, and go back and look at certain parts later. But most importantly, there are assignments at the end of the talk, and I do recommend that people do these. They're pretty trivial. They're like cleanup level type stuff, and it's just designed to review a few parts of what did we go over and put things into practice. It's definitely easier to learn something when you actually go do it instead of when you just have it go in one ear and then out the other and then have the rest of your day. You're welcome to send any CLs for this stuff to me. I will review it, or to an appropriate owner in question. So finally, what's in this first part of this series? The what is this series part, which we just went over, and then copy and move operators, lvalues and rvalues, and stdmove, and then finally the assignments. So jumping right into copy and move operators. So what are these? These are basically the garbly looking signatures that you'll find between a constructor and a destructor in the class. You can see here we have the copy constructor and assignment and the move constructor and assignment here. They have lots of ampersands on them. If you don't know exactly what amper means, that's okay. We'll explain that later. I've listed these between the constructor and the destructor because that's what our style guide says to do with them. You might not find these in every class because sometimes we want them to be not there, and we've used a macro called disallow, copy, and assign in the past. But if you do see these in a class, this is what they'll look like. So you should think of construction and assignment, that is the top two and the bottom two, together. So whatever you do for one, you should do for the other. If you delete one, you should delete the other. If you default one, you should default the other. In this case, you see that the signatures, we've deleted the copy, constructor, and assignment operators, and we've defaulted the move constructor and assignment operators. If you don't do this, and by the way, not all of our code does this, so don't expect that we get this right everywhere. Your code either might not compile when it should, or much more likely it will compile, but it will be at risk of very subtle bugs in weird cases that you don't want to have to track down because they're ugly. So the rule of thumb is just construction and assignment always do the same thing to each one of those. Copy and move, you don't need to do the same thing as each other, so we'll get to that. You also should always say what you're doing with at least one of them. So if you define or you delete one of these pairs of things, it will implicitly delete the other. And the most frequent pattern you'll see is that we delete the copy ops and we don't say anything about the move ops, which means they're implicitly deleted. The object is not copyable or movable. On the bottom, you see an example of not saying anything. What is this class? Is it copyable? Is it movable? You don't know. I mean, there are rules in C++, but you don't want to have to remember these as a reader. So just always say something with one of the pairs. And if you need to, say something explicitly with both of the pairs. Generally, you should make your class copyable if it's a sane concept. Once again, this is not necessarily what we've always done in the past, because the old style guide a couple years back kind of preferred the opposite. It basically said make everything non-copyable unless you really need it to be copyable. So a lot of our classes delete copying. Current recommendation is go ahead and make it copyable if that's like semantically sane and meaningful and it's not going to introduce bugs. So this is what it looks like to make a class copyable. You write the two copy ops, the copy constructor and the copy assignment operator, and you default them. And remember here, because we said anything about one pair, even though it's not a deletion, it's a defaulting, that means the move ops, the other pair, is implicitly deleted. This is kind of a gotcha, because you might think like, oh, I defaulted one, so it implicitly defaults the other. No, that's not how it works. Anything implicitly deletes the other pair. One reason why you should make your class copyable by default when it's sane is because you need that to be able to store it in a vector or a lot of other containers. The people who know C++ better in the room might be waving their hands saying, oh, but you could put it inside a unique pointer. And like, yes, there's ways around this. But in general, if you want people to do common things with your class, making it copyable helps them to do that. Now, movable, which is a trickier concept, is basically copyable, but it assumes that you're not going to ever read the source object again before you destroy it. So I'm going to say that again. Movable is actually copying, but it assumes you won't read the source again before you destroy it. So that allows you to leave the source in any state you want as long as it can be destroyed. So we'll explain later why that assumption is reasonable. I just want you to have the idea that that's what moving is it's copying with an assumption. You still need to leave the source in some kind of valid state. So in other words, you need to be able to run the destructor on it and it won't break something. So here's a little swath of example code. We're creating a new array of 3 ints. And then we have a move constructor that does a pointer copy, a shallow copy of that array. And we have a destructor that deletes the array. And this is problematic because a move is a copy with an assumption. So we've assumed that our old object isn't going to be read again, and we copy the pointer. Now we destroy the old object, or we destroy the new object. Either way, we call delete on this pointer. And we still have one of these two objects with a pointer to memory that's now dangling. So this is basically going to be a double free, because as soon as we free the second object, we're going to die. You can get into similar trouble with bad ref count handling. If you have like a ref counted member or something and you do a move and you don't increment and decrement properly, basically you could end up like freeing your ref counted object. So the upshot of this is when you move, you can't just assume like the source magically disappears from the universe. You have to leave it in some state where destroying it is not going to break things. But other than that, you're free to do what you want to it. Okay, so I just gave a bunch of information on like what moving is, that it's copying with an assumption, but why do it? Well, for one, it allows you to do something that's new in C++ 11, which is now old enough that those of us who've been programming since 2011 hopefully have seen these before, but it allows you to do something called move-only types. So an example of this is unique pointer. There used to be a type in C++ called auto pointer. It couldn't be used safely, and basically the reason it could not be used safely is because the language did not have this concept of moving at the time. So a move-only type is very simple. It is designed to ensure that only one copy of a particular instance exists at any given time. If you have an instance of class C and you move it, then basically the new thing is the one and only, and the old thing gets destroyed. And then if you move it again, now, the yet another new thing is the one and only copy. So this move only type can't actually be copied. You can't copy your instance to another thing and have them both sitting side by side. You can only move it. This turns out to be useful for a number of reasons, which I'm not going to go into right here, just to say that that's a thing. The other reason why you want to do moves is that it allows higher performance copying in some cases. Not every case, so moving is not like just some magic fairy dust that you sprinkle over stuff and it makes all your code faster. But for certain objects, assuming that the source doesn't need to be usable anymore gives you some benefits. So here's an example, again, with that array of 3 ints. A more compelling example might have a much larger array, but this is sufficient to show the idea. If you write a copy constructor, then instead of just doing a pointer copy, you actually need to do a deep copy, which is what this code is trying to do. So it does a mem copy from your old array into the new array and does everything. Well, that's slow because you need to read the whole big block of old memory and write it into the new block of memory. And if you have like 10 billion ints instead of 3 ints, that's probably not something you really want to be doing. When you assume that you don't need the source anymore, then you can actually get away with the pointer copy. And the difference between this and the bad example that I showed previously is actually the addition of this little c.array equals null pointer statement on the second to last line. Setting the old object's array pointer to null means that when we delete it, we're not actually going to free that thing, so we won't get a double free anymore. That's how we fixed that bug. But the concept of just doing a shallow copy here is valid. Various different STL types fall into this kind of category. So anything that stores its data like in the object itself. Std vector, std string, there are other things. And of course, in Chromium, we have all kinds of objects like this that are potentially expensive to copy. So they have move operations supported for performance reasons. So just to hammer the point home some more, there's no magic faster like move operation in memory. There is a call called memmove that doesn't actually do the same thing as C++ moving. So if you've seen that, like, don't think, oh, that's how they implement move, is they do a memmove call instead of a mem copy. No. under the hood, it's still just a copy. You're copying member state, or you're deciding not to copy member state. It's really just doing that copy with an assumption that allows you to get away with stuff. And that means that sometimes you can or should support moves that don't actually do anything different than copying. So all the basic types, for example, int, support moves, but moves are just copies. So you can move an int and it will leave the old int in place. Some people see a move and think, oh, okay, the source is definitely destroyed. No, that's not true. If you wanted to say that, you would actually have to guarantee that you wrote like trash over, or null or something over the source object. And since performance is usually the goal, like the whole point is to not write to the old object if you don't need to. There's a few miscellaneous extra things that I want to say about copying and moving before we go on. The first is you should try to use equals default for things that you want to allow if you can do it. Some of our code that say doesn't need to do anything special on like a destructor writes just a little empty pair of curly braces instead of equals default. Equals default is a little more explicit, and in the case of things like destruction, it can actually produce more optimal code, surprisingly. But you need to be careful that equals default will do shallow copies on pointer members, and this may not be what you wanted. So this is going to produce something like that double free problem for that manually memory managed array case that I was listing before. That's a case where you would have to write out your copy manually. There's something called the rule of 3, 5, or 0 that is pretty much you can either default your copy and destruction, your copy, move, and destruction, or none of them. So 3 things, 5 things, or 0 things in terms of the number of signatures. And what they're really trying to say there is, hey, if you go write any of these and you start to write manual code, like in your destructor, you have to manually delete or free some memory, or you have to do anything else special, you should immediately beware of using equals default on things like copies and moves, because you probably have to handle that kind of thing there too. On the other hand, if you can write one of them safely using equals default, then you can probably write all the ones that you want safely with equals default. Okay, that was a whole ton of like just random factoids crammed into a small area. Any questions before we go on?
I think it'll be good to talk about release, which is evilly named.
So like on a reference counted stuff, or do you mean like unique pointer release?
Yeah, because it's like, oh, I'm setting you free, but no, it's just like not freed. I've seen bugs like that.
Yeah, there's a whole long area that we can go into here with, in general, memory management and RAII. That's actually going to be in another talk. So the short summary is, if you want to keep something in a scoping object, you should be very careful about mixing that with raw pointers. And anything marked release or .get gets at a raw pointer version of that scoping object. It becomes very easy to do things like all of your move and copy, double freeze, and other problems, as well as memory leaks, etc. So you should do the stuff that I talk about in the RAII section of a future talk. In the chat, can you explain why we have rules to add curly braces instead of equals default in some cases? I'm not actually familiar with what rule that is, so maybe you could give an example of that, or somebody could remind me. And in the meantime, PBoss says, maybe you missed this. I'm just going to call this out because I'm not going to say anything more on this. Maybe you missed, you might have said this, but if you have a move only member, that implies your object is move only. Yes. Like if you stick a unique pointer in an object, then that object itself is going to be move only or not movable.
And in particular, move onlyness like infects the object graph. So like anything that holds a move only object is itself move only. So there are big areas of the Chromium codebase where nothing is copyable because like you have a move only basic type somewhere in there.
Yep.
There's also like, if you specifically work with UI, which I happen to do, like all of the view hierarchy is move only. So if you happen to work with essentially any part of something where your entire object model is move only, the default assumption to try to make things copyable may not apply to you.
Yeah, so in these cases, we're pretty much in case one of the reasons to make something movable, which is move-only types, and you might have a lot of them. They're fairly common.
It is a highly reasonable design approach, though, to try and isolate a bunch of your data into a copyable type and then have the move-only type encapsulate, like, not that, so that you can still have a copyable model type that sits around. That's
yeah, this is a little bit like the pointer to impl idiom, but we're definitely getting a field of C++ 201 level content, if I say that. So,
regarding that question about kind of requiring the curly braces, I think the example I remember is when the object has some sort of like complex, like it inherits from something. So rules that it has to have like it can't have it has to have like the constructor body in a CPP as opposed to header, and that's kind of.
I think I might get this one. Yeah, essentially what Dana wrote. Peter, you want to take this? I'll shut up.
Yeah, so very briefly, if you try to equals default things, you need to do that in the you can do that in the definition or the declaration. The definition is the part of the CPP file, and the declaration is the part in the .h file, to oversimplify it. If you do it in the declaration in the .h file, then you may get warnings from our style plugin saying, hey, you made some big class like copyable or something, and you did it in line, and now the code is too big and I'm unhappy, and you will get very confused. And the way you solve this problem is that you put all that stuff in the .cpp file. But you can write like copy, move, and destructor equals defaults in the CPP file, and I encourage people to do that. And then finally, and I'm going to move on after this for time reasons, how to decide whether making a class movable versus using unique pointer. Gosh, I don't know that I could cover that without saying it depends on the case. I would say in the abstract, make your class copyable and movable if those make semantic sense and would in theory like be beneficial to coders. So like if you have a bag of data and it's not going to cause weird problems to copy it, make it copyable. You know, if it's going to provide a performance improvement, make it movable. If you still stick it in the unique pointer later, big deal. Like that's okay. You haven't really lost anything. So I think the two decisions are a little bit separate, because one is basically the decision is made on the side of where you implement the class, where you design the class, and the other is made like at the usage point, where you decide like, how will someone else refer to this class? But those two things definitely do both get considered at the same time.
I think maybe one good example of like when to not make it copyable is like if something else is observing the object, or you have a lot of like dependencies outside the object itself, where it's like if you make a copy of it, then should your observers also be copied? Do they now observe both things? And when you run into like any complexities like that, it feels good to just bail out and make it not copyable at all, to not have to solve those problems.
And in many cases, those cases aren't going to make semantic sense to copy anyway. So like a web contents doesn't really make a ton of sense to copy, because what does that mean? You're like copying the whole web page or something? I mean, maybe in the context of calling like duplicate tab, you might in theory want to do this, but that seems like a very complex thing that it is hard to reason about. And that's kind of a clue that that sort of an object probably should not be copyable.
Maybe something like that is like, if something can like semantically refer to you, then spurious copies of you may be a real problem.
Okay, so totally going to move on at this point. lvalues and rvalues. Why go over this? Because this sounds like C++ 401 or something maybe. You know, why dig deep into the grammar of stuff? Well, for one, we're going to oversimplify the real C++ grammar. I'm not actually going to give you the definitions that are on Wikipedia. C++ has X values and GL values and PR values and all kinds of things. And I'm totally going to elide that, because I'm basically going to give you the thing that makes sense for me to think about instead of like the real truth. It is the Bohr model of the atom kind of thing. But it is valuable to go over this stuff because it makes understanding what moving does much more clear. And moves are the tentpole of C++ 11. So the question here is, can anybody tell me in like one sentence, what's an L value and an R value? If you don't know, guess. I'm hoping for wrong guesses, actually. So definitely guess.
An L value can be assigned to.
Cool. An L value can be assigned to. Other guesses? Everybody's like, that sounds good. L value has a name. R value is used to move. L means the left side of equal. Okay, so good. We've got a couple of the different things that I'm going to go over here. So I'm going to go over a few like common sort of misleading impressions of what these are, and then the one that I think is accurate. So L value is on the left side of an assignment. L value can be assigned to. The reason I think this is wrong definitions is a little strong here. Sorry. I should have just said like misleading. The reason I think this is misleading is because if you look at like X equals Y, okay, X is on the left of the equal sign, Y is on the right of the equal sign. Therefore, X is an L value and Y is an R value, right? But in actual fact, both of these are L values. And in the case of calling a function with X, X is an L value. But how would you know that if like X can be assigned to is your rule? Because like there's no assignment going on here, so you're not really sure like what's being assigned to, if anything. If the func isn't writing anything to X, is X not an L value? Not sure. So there is actually some truth. All of these definitions have some truth to them, but I find them misleading, and that's why for this one. L values, things you can write to. So this is kind of a different way of phrasing that one. Well, the reason this one's misleading is for reasons of constness. If you have a constant X, X is still an L value. If you then pass it to a function, then X is still an L value there. And finally, if you pass a const ref to a function, X is an L value there. And in all of these cases, you can't actually write to X at all. You can't assign to it, but it's still an L value. There's also one that no one mentioned, but I have seen before, which is R values are things with that weird double ampersand on them, and everything else is an L value. This isn't right either. It might surprise you, but in this function declaration here, func takes an int ref X, and X is an L value, actually. It's not an R value. So the correctish definition, which a couple people did say, is basically L values have a name. So if we call X equals foo of Y, X and Y both have names, namely X and Y. So they're L values. foo of y returns something here, but it's not named. It's just used to write into x. So the return value of foo in this case is an r value.
PK, is foo also an L value itself, like the function?
Punt, because I don't actually know the answer to that. I don't think so. Dana says no, and I trust Dana. I should have noted at the very beginning that I'm giving this talk, but I'm far from like the C++ expert on this team, and there are many people on the team who know more than I do, so I will be happy to hear corrections from them. So yes, going to trust my audience here and say no, it's not an L value because it's not a value. Here's another example. If you declare A, B, and C as strings, then they're all L values because they all have names, A, B, and C. But if you then add them together, A plus B plus C, to append the strings into one big long concatenated thing, that big concatenated thing, and in fact the intermediate concatenated thing when you do A plus B, are all R values. Ellie is like, I want to stump Peter by writing things.
Sorry, I'm asking Dana.
So going to ignore that. Here, interestingly, we find a case of a bug, and I've written this bug. Maybe you have too. The bug where you meant to write some kind of an L value, and you accidentally wrote an R value. So in this case, if you try to declare an object M of type myClass and you give it some arguments for its constructor, you just declared an L value. If you forget the name, you declared a standalone R value. That's totally legal syntax. But it's probably not what you meant, because it's going to go away in a minute. And this is going to get at something I'll say in a minute about R values. So typically, R values show up as the result of doing a function call or executing an operator. Generally, they die at the end of the expression, whereas L values die at the end of the enclosing scope. So when you have this code, int x equals 3, and then you call foo of x, x is going to die at the end of the scope because it's an L value. The R value you get from calling foo is going to die, and I'm assuming foo returns something here, is going to die at the end of the statement. Now, this is really exciting. Wow, what did I write on this slide? I'm like confused by my own notes. Oh yes, I'm clarifying here. I wasn't actually going to go to that point yet. Even if you have references, references don't really change the nature of L value and R value-ness. So you can have an L value that's a reference to something. You can have a function call that binds that L value to another L value or to an R value. And so just because something is, say, bounded by, or shouldn't read chat while saying words. Just because something is an L value or an R value and it's bound to the other type doesn't somehow flip it. This also gets at the case I mentioned earlier where you have this double ampersand. Here, x is an L value with type reference to R value. If you call func of something, then you must pass in an R value. But x, the type that receives it, is still an L value. So even though x has type reference to R value, x is an L value. And that means that, like, sometimes you can write functions that can't call themselves recursively easily. I think, yes, I have this example here. So if inside func, I just try to call func again with the thing that's passed in, it won't actually compile. So again, amper does not mean this is an R value. It means this is an L value that has type reference to R value. So how do you get this to compile? Well, that's part of why we're going over lvalues and rvalues, is to make it clear like that you want to do something to make this compile. Yeah, I'm gonna skip over that slide. No, I'm not gonna skip over that slide because I have multiple slides on it. Okay, sorry. So if you have a single ampersand on a parameter, it can bind to both lvalues and rvalues. It doesn't just bind to lvalues. And if you have a double ampersand on a parameter, it binds only to rvalues. There's also lots of other things. There's ref qualified members, there's template context. So like ampersands mean lots of things, but this is what double ampersand means for our purposes, is matches rvalues when you put it on something. And single ampersand means matches both. There's reasons why it doesn't mean just matches lvalues. It turns out that's not what you want. Now we're going to do the exciting thing of moving rooms while talking and carrying stuff, because I'm talented. This explains the copy and move constructor signatures. Thank you. Because if you have a copy constructor, it takes a single ampersand reference, which is, it binds lvalues and rvalues, but then you have a move constructor that takes the double ampersand, which binds to just rvalues and is preferentially chosen for rvalues. So these die at the end of the calling expression. And this is why move operations can assume that the source isn't going to be used afterwards, because rvalues are going to go away like right after you call the move constructor. The copy constructor that you're going to pass an L value to, or possibly an R value if you don't have a move constructor, has to copy because it can't make that assumption, because maybe the source is in fact going to live longer. I feel like my thoughts were very scattered during that, and thus probably my words were very scattered. So before I do stdmove, is there anything where I said a bunch of stuff and people went, huh? And want me to say it again in a clearer way? Okay. Either I'm awesome or we're running low on time and I don't care. So stdmove. So this was the whole reason why we went over L values and R values. So some review. If you have a class C that's copyable and movable, then a function that takes a C amper binds to only R value Cs. You also have a function that returns a C by value. That means that calling the function on the temporary, the R value that you get from calling return C will compile. Calling it on some like actual named variable, i.e. an L value, as we have in red here at the bottom, won't compile. Hopefully it's clear why this happens, because we can't bind the R value parameter reference to this L value. So how do we make this compile? Oh, let's see. What did I? Ah, yes. Okay. Well, one way we can make it compile is we can change the function to take a parameter by value instead of by R value reference. So now, if we pass in an R value, then we will call the move constructor, because that's what preferentially gets bound here. And then we'll construct a new temporary, which itself is an R value because it's unnamed, and we'll pass that in to the function. Or if we call it with an L value, we'll call the copy constructor. This is maybe great because it works, but maybe not great because it seems inefficient. We're calling like the move constructor or the copy constructor or something like that. And probably like if C is a big object, like we want to ensure we don't call copy constructors all the time. So maybe this isn't the right way to go. So this slide is simply asking the question, how do we make the one case compile and the other case efficient, since we prefer moves to copies? The answer is stdmove. So stdmove is actually kind of a misnomer. It does not move anything. It's a cast. Specifically, stdmove probably could have been called like std rvalue cast, and it would have been less misleading, but it also would have been like really long and hard to say and type and stuff, and that's kind of annoying. So all this does is it takes your L value and it declares to the compiler, no, in fact, this is an R value. Treat it like an R value and, you know, bind, etc. It is an R value. So thus, it makes things eligible for move ops because your move constructor is simply a constructor that binds preferentially to and only to R values. This generates no code. Since it's just a cast and it doesn't have to like fix up the this pointer or do any of the other things that potentially static cast can do, it doesn't actually result in doing anything. It just changes how something gets evaluated by the compiler for function binding. And that means that it doesn't modify the argument's lifetime. If you stdmove X, that doesn't mean you just destroyed X. And it also doesn't mean that you caused X to be destroyed at the end of that move call. If you have a unique pointer and you call stdmove on it in like just as a statement, you don't do anything with that moved thing, you just do a stdmove alone, that's legal. It's fine. It's meaningless. It does nothing, and the unique pointer is not reset. If you have a once callback and you call stdmove on the once callback, but you don't actually run it, it's not null. What stdmove does do is basically assert to the compiler that you're not going to read the argument again before destruction. You're asserting that the things it cared about for R values hold true. And so in this case, you have you're calling like stdmove with X and then using X in the next line. This is almost certainly a bug. Even if it's not a bug now, it will be a bug in the future because you're violating the constraint that you just said the compiler could assume. Yes, Ellie notes that if you do stdmove as like a function argument, then because of order of evaluation differences, this can be a problem. So now with stdmove, we can make these cases work like we want. So we can use stdmove with things that only accept R values to accept an R value because we can cast them to an R value. And we can use stdmove to use the move constructor instead of the copy constructor in cases where we pass by value. Hopefully these aren't actually the same C in these examples because otherwise you just introduced that bug. Stdmove is not helpful unless you need to convert an L value to an R value. This is kind of like what I said about do not magically assume that using moves everywhere makes your code faster. Don't assume that just calling stdmove on everything makes all your code faster. If you already had an R value, like in this first bullet here, the return value from a function is an R value. Calling stdmove on it doesn't do anything. It's already an R value. If you have an object that is not movable, calling stdmove on it casts to an R value, which is legal, but it's not going to help you because you're not going to bind differently to anything. And then finally, if your function is accepting like an L value ref, calling stdmove to make it an R value isn't going to change how your thing gets passed to the function. So all of these are cases where move is legal but pointless. And unfortunately, the compiler will not warn you that you've done a legal but pointless move, or at least I don't think it will usually. Also, David asks, does the compiler tell you if you touch a value you previously stdmoved? The answer is sometimes, but don't assume that it will. assume that the compiler will not always catch you in this case. So stdmove is actually kind of dangerous because it asserts something that you now need to make sure is true. I feel like I'm ramming the point home here, but stdmove is like really unclear to a lot of people, so I'm going to kind of hit it from several angles. And we are almost done. I know we're running low on time here. Stdmove has no effect by itself. If you see in the abstract stdmove of x passed to a function, you don't know what that does. You don't know that it results in moving x, but you also don't know that it doesn't result in moving x because it depends on what func is doing. The upshot of this is if you see a stdmove, you don't worry about the move call. What you worry about is what's using the move call, and that's what tells you what's going to happen. Something that just came up in chat, so good timing. You should generally avoid using stdmove when returning things. And I'll only briefly say why, because it's 301 level. The brief reason why is it defeats the return value optimization. So don't do it because it makes your code worse. Also, this is a usually and not an always, because sometimes you actually do need to return stdmove of something. The compiler will yell at you if you need to do it. So the rule of thumb you should use is never do this until the compiler tells you you have to do it, and then only do it then. Okay, that actually covers all of the material that we're going to go over today. So before I jump into assignments, are there any questions people want to ask about stdmove, lvalues and rvalues, and copy and moves and how they get invoked?
Now I'm curious about the situations where you need to return stdmove object. When does it appear?
It's basically when you have a non-copyable object that you're trying to return. Sometimes you need to explicitly stdmove it. It's that plus some other constraint. I can't remember off the top of my head. People like Jeremy Roman know this stuff. Other questions?
This isn't a question, PK, but I want to say this talk is really excellent, and I now know what the double ampersands mean on function parameters, and that I should stop littering my code with stdmove. So thank you very much.
Oh, you're welcome. Okay, Robert gives an interesting thing. So a moved object is meant to be left in a valid state, right? So it's valid to do a subsequent assignment. So the question is basically, can you do something like stdmove x and then x equals blah, blah, blah? I would give the answer, don't do this. I think it will work. But I still think it's unclear. Basically, because you're kind of saying X is not red again before its destruction. And then you're saying, oh, no, wait, we're just going to write a different value over it and then keep using it. I would simply use a different object to do this. And that way, not only do you not need to worry about whether this is safe, but like somebody reading your code with the assumption that I had in mind, which is like, oh, I saw stdmove, this thing is totally dead from here on, won't like get confused and you won't refactor code later to make it broken. If your function or method is taking a copy of an input variable, is it better to receive it by value, ref, rvalue? This is actually going to be covered in a upcoming talk. So I will have some rules of thumb for that later. Okay, I'm going to go over the assignments. So here's some assignments that you should consider. First one, fix 5 disallow copy and assign. So we actually have an open bug on this macro is deprecated and we should change over to explicitly declaring that things are not copyable and not movable by using equals delete. Now, if you remember, I said that once you declare, say, the copy ops as equals delete, then the move ops are implicitly deleted. So you don't have to delete all 4, just 2 of them. So fix 5 of these means go find 5 of them, change them to explicitly deleting the copy ops, put that between the constructor and the destructor, and be done. Second bullet, make 5 constructors or destructors use equals default. Now you can do this in the declaration, in the header file, and you should if you can get away with it, generally. But if the Clang plugin warns you that you're now inlining a complicated thing, then you will have to go do the equals default in the .cpp file, and that's legal. So go do that. Fix 2 classes that define one of construction or assignment, but not the other. So the case for this is when you look around and you see like somebody's defined a copy constructor, but they haven't defined copy assignment. Or they've done the other thing, they've defined like a move assignment operator, but not a move constructor. Like I said before, this will usually compile, but it's dangerous. It lets your code break over time. So go fix that. Finally, the last bullet, add movability to a class that could benefit from it. So this requires that you actually go look and see, like, is my class not being moved right now, but it could be moved, and it would benefit from being moved, maybe because it contains a whole bunch of data inside it. It's really big, and maybe we're copying it today. Or maybe we're just like being forced to store it in a unique pointer today, but we really kind of wish that we didn't have to do that, and go add move ops to it. The extra credit on this one is then also go add stdmove to the right cases where we use the class. And you'll recall that that means things that are lvalues but need to be cast to rvalues so that they will start invoking the move constructor or move assignment. So if you do any of these, like I said, feel free to write them into CLs and send them to me. I will be happy to review them. If I'm not an owner, then we can get them landed via another owner or something. Last questions, because this is my last slide. Okay. Seems like everyone is thoroughly impressed and amazed and excited. So go forth and move things.
Great job. Thank you, Peter. The recording and the chat will be available on Go Brews Bites later today as soon as I get it. And Peter, they can reach out to you if they have any questions?
Oh, yeah.
Perfect. Cool. Have a great day, everybody.